Hello everyone. Today we'll discuss about serial communication in PIC16F877a microcontroller. So before going to discuss something about serial communication, let us see what is a communication. So communication is a transfer of information between 2 points, two systems, two machines, or two terminals will be considered as a communication. Okay. So before going to the communication inside or serial communication inside this controller, let us classify this communication now. Now it has been classified into two types, that is parallel communication and the other one is serial communication. So parallel communication is nothing but transferring multiple bits at the same time will be considered as parallel communication. And coming to serial communication, here a single bit is transmitted for every time. So or at every time only one single bit is transmitted. Okay, so that is nothing but a serial transfer. Okay, now it has a parallel transfer has its own advantages as well as serial transfer has its own advantages. Like if we are choosing parallel transfer, then the data is transmitted as faster, and then it is expensive for implementing, and it is only used for short distance communication. Because if you are using it for long distance communication, then there might be a problem of noise. Okay, and when it comes to serial communication, here the data is transmitted very much slow as compared to the parallel, and then it is cheaper and short and long distances. So we can use this kind of communication for short communications or for long distance communication. Okay. Now let us classify the types of this serial communication. Now it has been classified into two types. As we are talking about the serial communication, so I'm just classifying only the serial communication here, like synchronous and asynchronous. Okay. Now in case of synchronous, the data is transmitted along with the clock, but whereas in asynchronous, only the data is transmitted. Okay, and let us see some technical terms inside this synchronous communication. Now the device which generates the clock is termed as a master, and the device which receives the clock is termed as a slave here. Okay, but whereas in asynchronous communication, we call our device which is sending the data as transmitter, and the device which is receiving the data as a receiver. Okay, so here master and slave, and here transmitter and a receiver. Okay, so master will generate the clock, and slave will receive the clock. Okay, now as we are intended to learn about asynchronous communication, let us see some of the principles of this asynchronous communication. Like no clock is transmitted. As I've already told you that only data is transmitted, and the data rate or the baud rate is fixed here. We cannot change the baud rate during the communication process, and we have to use accurate and stable clock sources. Why? Because during communication, if any variation is occurred inside the transmitter or else on the receiver, then it will result in loss of data. Okay, so that is the reason we have to use accurate and stable clock sources at both the ends. Okay, and each byte or word is framed with start and stop bit. So the complete message bits are the complete message bits will undergo one process, and that process is called as framing. Okay, and the output of framing process is termed as a frame, and inside the frame we have the message bits along with start, stop, as well as one optional parity bit is added to the original message bits. Okay, let us see how it looks like. Now this is how the original frame looks like. Initially the line would be idle. Okay, the transmit or receive line would be idle, and then as you can see, initially the start bit is transmitted. Okay, so the start up to the stop is nothing but your frame. Okay, start bit and data bits, and then a stop bit. Okay, now the start bit indicates the start of the frame. Okay, and the first data bit, that is your MSB, and then the last data bit is your LSB, and then stop bit indicates it is the end of the frame. So start bit always represented with the help of a logic low signal, and the stop bit is always represented with the help of a logic high signals. Okay, and technically we call this start bit as a space signal, and stop bit as a mark signal. Okay, so if I want to transmit, assuming that I want to transmit two characters like A and B, so initially A is framed as well as B is framed. So A will have its own start bit as well as stop bit, and B will also have its own start bit as well as stop bit. So in case of asynchronous communication, start bit indicates start of frame, and the stop bit indicates end of frame. But whereas in case of synchronous communication, start bit indicates start of communication, and stop bit indicates end of communication. Now if we talk about the peripherals inside this PIC, we have two serial ports. One is MSSP and the other one is USART. So MSSP will provide us two protocols like I2C and SPI. Now these two protocols will come under synchronous serial protocols. And now we are talking about USART. So it provides only one kind of protocol, that is RS232. Okay. So let us see this USART in detail. Now we can operate this USART in three modes. One is synchronous master mode, and it is half duplex, and the other one is synchronous slave mode. It is again half duplex, and asynchronous full duplex. So you can only go with full duplex in case of asynchronous mode, but in case of synchronous, you can only go with half duplex communication. Okay. So in half duplex or in synchronous mode, one of the device would be acting as master and the other device would be acting as slave. Okay. And half duplex in the sense only one device can transmit the data and the other device has to receive the data during that particular time. Okay. And in case of asynchronous, as it is full duplex, so both the devices can transmit the data at the same time. Why? Because they have independent lines for transmission as well as for receiving the data. Okay. And in order to use this particular peripheral, we have to program some registers, or we have to access some registers, as you can see here: TXSTA, RCSTA, and then STBRC. So these are the three registers which we need to configure before using this UART. Okay. So let us see in detail about each and every register. Now TXSTA is nothing but transmit status and control register, and its address is 98H. Okay. So we'll see the importance of each and every bit here. Now we'll start with the MSB bit, that is clock source select bit. Now here this particular bit should be used only in case of synchronous mode, and this bit is used for making the device to act as either to act as master or else to act as slave. So if you want to use the device as master, then this particular bit should be programmed as 1. Okay. And if you want to use the device as slave, then this should be programmed as 0. Okay. And this bit is only used in case of synchronous communication, but not in asynchronous communication. Why? Because in asynchronous communication there is nothing like master or else slave. Okay. And then you have the next bit is PX9. So if you want to transmit 9-bit data, then it is enabled by programming this bit to logic 1. Now if you want to transmit 8-bit data, then you have to program this bit with logic 0. Okay. Generally in the real world we use or we represent every character with the help of 8 bits. Okay. And it is nothing but your ASCII representation. But when you want to transmit 9-bit data, so 9-bit is used in case of we want to send the parity bit, then that bit will be considered as the 9th bit. Okay. Or instead, in the other case, if there are multiple devices are connected to the USART bus, now each and every device is having its own address, then the transmitter wants to select a particular device. So in those cases, we'll be using this 9th bit as a address bit. Okay. So in that particular case, if this 9th bit is logic 1, then it means that it is transmitting the address. Okay. We'll see that. And if it is 0, then it means that it is transmitting the data. Okay. So if you want to enable 9-bit transmission, then this particular bit should be programmed as logic 1. And if you want to enable 8-bit transmission, then you have to program this bit to logic 0. Okay. But in both the cases, we'll be using ASCII representation for representing the data. Okay. And then you have transmit enable. So if you want to enable the transmitter block, then this has to be programmed as logic 1. Now if you want to disable it, then make it as logic 0. And USART will provide us synchronous as well as asynchronous communication. So if you want to use synchronous communication, then this has to be programmed as logic 1. And if you want to use asynchronous communication, then this has to be programmed as logic 0. Okay. And then you have BRGH, which is nothing but high baud rate select. So if you want high speed communication or high speed data transfer, then you have to program this bit to logic 1. Okay. And if you want low speed transmission, then you have to select this bit as logic 0. And this is used only in case of asynchronous communication, but there is nothing like high speed or low speed transmission in case of synchronous communication. Okay. And then you have TRMT. Now this particular bit we have to monitor while transmitting the data. Okay. And this will give you the status of the shift register. Whenever the shift register inside the transmitter block is empty, then this particular bit will become 1, indicating that the shift register inside the transmitter block of UART is empty. Okay. So we have while transmitting the data, we should monitor this particular bit. Okay. We'll discuss about that when we come across the block structure of a transmitter block. And then we have PX9D. Now this is the 9th bit of transmit data. Okay. So if you want to transmit the 9-bit data, so you will enable that with the help of this bit. But that ninth bit should be placed inside this particular bit. Either it might be 1 or else it might be 0. Okay, so enabling of 9-bit transmission is done with the help of TX9, and placing that ninth bit is done with the help of this TX90. Okay, so CSRC for selecting the device either to act as master or else a slave, and TX9 for making or enabling the 9-bit data transmission or else 8-bit data transmission, and TXEN for enabling the transmitter block of UART. And then you have synchronous. If you make it to 1, then it means you are using synchronous communication. If you make it to 0, then it means you are using asynchronous communication. And then for high speed or low speed baud rate, you have to use this bit. And then you have TRMT. So we have to monitor this bit while transmitting the data, because it will give you the status of the shift register. Okay, and then you have TX9D. So if you want to transmit the 9-bit data, then 8 bits should be placed into one buffer register, and the 9th bit should be placed inside this 9th or else this particular bit. Okay. Then you have RCSTA, which is receive status and control register. Okay, so we'll again start from the MSB bit, that is SPEN. Now, if you look at this, when you want to use USART communication, then we have to use GPIOs. So those GPIOs should be configured as TX and RX in case of UART, and in case of USART, they should be configured as clock and the data. Okay, so if you want to configure them as USART pins, then you have to program this particular bit to logic 1. So if you program these bits to logic 1, then the port C pins RC7 and RC6 will be acting as TX and RX. Okay, if you are programming it to 0, then it means that those pins will be acting as GPIO pins. By default, they will be acting as GPIOs. Okay, so when you want to use USART in your application, then you have to program this bit to logic 1. Okay, and then RX9. Okay, so if you make it to 1, then the receiver will receive the 9th bit. If you make it to 0, then the receiver cannot able to receive the 9th bit. It can only receive only the 8 bits. So while transmitting, if you are making this bit to 1 and you are transmitting the 9th bit, then definitely at the receiver you have to program this bit to logic 1 so that the receiver can receive the 9th bit. Okay, and that received 9th bit will be stored inside this RX90 bit. Okay, so while transmitting, you have to place the 9th bit into TX90, and while receiving, the receiver will place this 9th bit into this RX90 bit. Okay, and then you have SREN and CREN. SREN for single receive enable. So if you want to receive only one single byte of data, then you have to enable this. And if you want to receive continuously until the stop bit is transmitted, then you have to enable this particular bit. Okay, and then you have address enable. So if you are making it to 1, then the 9th bit inside this RX90 will be treated as address or else as data. If you are making it to 0, then the 9th bit inside this will be treated as a parity bit. Okay, generally parity bits are used in case of error correction and error detection. Okay, so if you are making it to 1, then if this 9th bit is if the 9th bit received by the receiver is logic 1, then it treats it as a address. Okay, whatever the information that it has received, that is 8-bit information, that will be treated as address. Okay, if this 9th bit is 0, when this ADD-EN is 1, then the received 8 bits will be treated as data. Okay, and then you have 2 bits for representing the error conditions. Those are FERR and then OERR. So framing error and then overrun error. Okay, so framing error is generated whenever there is a modification inside the stop bit. Okay, and it means if there is any variation in the stop bit, then it indicates a frame error. Okay, so for example, if transmitter is sending one stop bit and receiver has received 2 stop bits, then it indicates a frame error. If transmitter is sending 2 stop bits and receiver has received only 1 stop bit, then again it indicates a frame error. So any modification inside the stop bit will result in a frame error. And then overrun error. Now this happens assuming that if the external peripheral wants to send 2 characters or 3 characters to the UART. It has transmitted 1 character. Now that character is placed inside one buffer, that is receive buffer. Now the processor did not read that particular character, so that character is present in the buffer register. Okay. Now as the status of this UART is as it is not known to the external peripheral, so what happens? External peripheral will send the next character. Now this next character is going to replace the earlier character or previous character. So in this case, overrun error will be resulted. Okay, so overrun error Whenever overrun error is generated, then this particular bit will become 1. So these two bits will give you the status of the error flags. Okay. And how to calculate the baud rate? So baud rate is calculated with the help of these formulas. And after calculating the baud rate, that value must be stored inside this SPBRG register. Okay. As similar we have done in case of ARM as well as in case of 8051. In the same way, we have to calculate the baud rate, and that value should be stored inside this SPBRG register. Okay. As you can see, in case of asynchronous, as I have already told you that we can go with high speed and low speed. So if BRGH is 0, it means you are going with low speed, and it will have one particular formula for calculating the baud rate. And if BRGH is 1, then it means high speed. Then you have the divider, that is 16, but instead in the previous it has 64. Okay. And you have F oscillator, whatever the frequency that you are giving, okay, through the crystal circuit, and 16 is a constant, and SPBRG is the value that you want, that you have to calculate, and then 1 is a constant, and baud rate is already known to you. Why? Because whenever you want to interface some peripheral, you would always read the data sheet of that particular peripheral, and you will come to know what is the baud rate supported by that peripheral. So baud rate is known to you. So F oscillator is known, 16 is a constant, and 1 is also constant. So you have to calculate this SPBRG. Okay. In the same way for synchronous communication, so there is no BRGH bit. Okay, as I have already told you that there is no high speed or low speed communication, and this is the fixed formula for calculating the baud rate. Okay. And then we have a PIR1 and then PI1. Okay. Now this inside this PIR1, we'll look about the bits which are related to serial communication, that is RCIF and then TXIF. Okay. So here RCIF will give you the status of receive interrupt. So whenever a character is received, and if it is stored in buffer, then this RCIF will become 1. Okay, indicating that one character is received, and that is now stored inside the receive buffer register. Okay, and this TXIF is the interrupt which is generated whenever the transmit buffer is empty. Okay, when the transmit buffer is empty, then this TXIF is generated. Okay, and as I've already told you that for every interrupt we have IF and IE. So if you enable this, then the processor will execute the ISR which is related to the UART. Okay, whenever this RCIF is generated, and in the same way, if you enable this, then the processor will execute the ISR which is related to UART when this TXIF is generated. Okay, so RCIF will give you the status of the receive buffer register while receiving the data, and TXIF will give you the status of the transmit buffer register. Okay. Now let us see the transmitter block internally, what actually is happening, and which bit we have to monitor. Okay. So user is going to place the data into this this buffer register. User can only access buffer register, so he's going to place the data into this buffer register, that is TXREG register. Okay, TXREG is our buffer register. Okay, now as soon as we place the data, now that data will be moved into this shift register. So as this TXREG becomes empty, then this TXIF will be generated. Okay, TXIF will become 1, which will generate an interrupt when TXIE is 1. Okay, so as this data is moved into the shift register, now this shift register will shift the data in bit by bit format. Okay, that is that will happen only when it receives the clock signal. Okay, so when it is going to receive the clock signal, we have to set the baud rate, and then we have to enable the transmitter block. Okay, then it is going to receive the clock signal. Okay, and if we are using 9-bit transmission, then 9th bit should be placed into this particular flag, and then it has to be enabled, so that this 9th bit will be moved into this 9th bit slot of shift register. Okay, so as it is receiving the clock signal, now it will transmit the data in bit by bit format by using this TX pin. Okay, and here TRMT, now this is the bit which we are talking about in case of PXSTA. Okay, that is I'll show you that. So we are talking about this bit, TRMT. Okay, so TRMT will give you the status of shift register. So whenever this shift register has become empty, then this TRMT will become 1, indicating that shift register inside the transmitter block is now empty. Now the processor can place one more character into the UART. Okay, now assuming that while it is transmitting the data, while shift register is transmitting the data, if you place one more character into this TXREG by monitoring TXIF, what happens? Then immediately this data will be moved into the shift register, so that the previous or earlier data will be lost or replaced. Okay, So that's the reason while transmitting the data, we should monitor TRMT but not TXIF. Okay, and SPEN, as I've already told you that if you want to configure this RC6 to act as TX, then definitely this has to be enabled. Okay, now let us see the receiver block. Now this is again similar. So receiver will receive the data through this RX pin, and that is happen only when SPEN is programmed to logic 1, so that this RC7 will now act as RX pin. Okay, now data is received, okay, and that is sent to the shift register only when we give the baud rate. Okay, so here the baud rate is divided by 64 or 16, that depends on that depends on high speed or low speed, and then this data will be moved into this shift register. Okay, and after getting the data, now here we have overrun error and frame error. If there is any differences in this overrun and as well as frame error, then they'll become 1. Okay, and we have to set this continuous receive enable to 1 so that it receives the data continuously. Okay, and after receiving the data, now what happens here? So this data will be moved into this RX-RG register. So as soon as this buffer has some data, now it will generate an interrupt, that is RCIF. Okay, and if this is programmed to 1, then an interrupt will be generated so that the processor will execute the ISR. Okay, and if this RX9 bit is 1, okay, and this 9th bit will be moved into this RX9B of, and here the buffer register is RCRG. Okay, so while transmitting data, we have to place the character into TXRG, and while receiving the data, we have to read the character from RCRG register. Okay, and here we have to monitor the RCIF flag while receiving the data. When this has become 1, then it indicates that RCRG is holding some data. Now the processor has to read that particular data. Okay, so this is how we are going to use this USART block for transmitting as well as for receiving the serial data. Okay, now let us see one example of transmitting one string here. So have took one string, okay, and I'm making this TRISC as 0. Okay, so TRISC as 0 is nothing but now port C is acting as output port. Okay, and then I'm writing TXSTA as 0x24. Now what does it make if I write TXSTA as 0x24? Let us see with the register. So TXSTA, now 24 in the sense 0. So as I'm using asynchronous communication, so I'm not going to use this particular bit, and 0, I'm not going to transmit 9-bit data, so it is only 8-bit data, and 1, I'm enabling the transmitter block, and then 0, which indicates I'm using asynchronous communication, and then so this completes 2, and the LSB is 4. So 4 in the sense 0, 1, 0, 0. So BRGH is 1, it means I'm going with high speed data transfer, and then TRMT is 0, it is a read only bit, we have to monitor this, and then TX90 is 0. Okay, and in the same way, I'm writing this RCSTA with 0x80. Let us see for what actually I'm writing this. Now 80 indicates I'm making this as 1, so it means I'm using serial port. Okay, that means RC6 and RC7 is now configured as TX and RX. Okay, and remaining all are zeros. Okay, now after configuring these control registers, now I'm placing a value into STBRG. Now this is the value or this is the value for giving 96 baud. This value will give us 9600 baud rate. Okay, and then as I have to transmit this string continuously, so I'm placing my program inside while 1. Okay, and I'm transmitting the character until null character is occurred, and that character is now placed into TXRG, and here I'm checking or monitoring this TXSTA. Okay, so I'm going to monitor only one single bit inside this, that is TRMT. Okay, as these are not bit addressable, so I have to monitor by using the complete register name. So that's the reason I'm monitoring this TXSTA. Okay, and whenever the TRMT becomes 1, then it comes out of the while loop, and then one more character will be transmitted. So this is how we can transmit the data as well as receive the data by using USART communication. Thank you.